Okay, so let's start. So we are now on chapter 9, and if you're going to look at this, we have already discussed the concept of ionic and covalent bonding in chapter 2. Okay, so the way that we're going to discuss this one is how do we differentiate ionic and covalent bonding. Okay, so whenever you hear the word bond, usually what's the concept associated to it? Usually we have what we call some sort of a connection. Okay? So how are these connections established in the chemical world? Okay? So we have this notion known as a chemical bond. It's just a strong attractive forces that exist between certain atoms in a given substance. So in the previous chapter we have what periodic table and the electron configuration. It give chemists the rationale for molecule and compound formation, and they found out that there are three types of these so-called chemical bonds. These are ionic bonds, covalent bonds, and metallic bonds. And if you're going to relate how we can recognize ionic bonds, covalent bonds, and metallic bonds from the periodic table, we just need to know what are the metals and the nonmetals. Ionic bonds usually the bond between metal and nonmetal. Ionic bond involves, we could say, transfer of electron. Okay. Covalent bonds, on the other hand, it is between nonmetal and another nonmetal. And usually, they can be the same nonmetal or different nonmetals. And it involves electron sharing. Now, the third one, so if you have a metal and nonmetal, a nonmetal and a nonmetal, so this is the one that exists within the metals. Okay? And the way that they have here is the so-called sea of electrons. And that's what makes metal a good conductor of electricity, because they have the electron that can conduct electricity. Now, we're going to go to them into details. Okay, at least these two. Now, ionic bond, that's a chemical bond formed by the electrostatic attraction between positive and negative ions. Okay? It forms when one or more electrons are transferred from the valence shell of one atom to the valence shell of the another atom. So this is where we have electron transfer. So if you're going to look at here, so you have Na reacting with chlorine. Okay, so if you're going to look at the electron configuration, which we discussed last time, so one of the electrons from the sodium was transferred or lost, and chlorine gained that electron. So when you lost that, what we call electron, you become positively charged, or what we call cation. If you gain an electron, you become negatively charged, or what we call an ion. So the positive and the negative charge that you have, that's form the electrostatic attraction. Okay? And if you're going to look at the new electron configuration, when you lose and gain electron, it is similar to what? The noble gases. So if you have here, they end up with an S2P6 number of the outermost electron, or the valence configuration. Now, there is a way to represent this so-called valence electron. So when we're talking about valence electron, that's the outermost electron. So if we're going to look at this valence electron, you can represent how many valence electrons a given element has. And credit goes to what we call Gilbert-Lewis, and that's what we're going to do today. How to write the so-called Lewis symbol. So a Lewis electron dot symbol is a notation in which the electrons in the valence shell of an atom or ion are represented by dots placed around the chemical symbol of the element. And the notion that you have here is the dots are placed one to a side until all four sides are occupied. So that means at most you have 8 dots. Okay, so that's the notion of the so-called Lewis symbol or Lewis electron dot symbol. Now it's easy for you to remember that if you have a periodic table, you concentrate on the representative elements. Okay, and each group in the representative element, whatever the group number that they have, that's the number of the valence electron. So group 1A would have 1 valence electron, group 2A 2 valence electron, 3A valence electron, and so on. Okay, so what have we learned from last meeting? Metals tends to form cation, non-metals tend to form anions, which means metal lost electron, and then the metal gained that electron. So if we're going to represent the transfer of electrons in forming calcium oxide from atoms, so all we need to do at the beginning is determine how many valence electrons each of these elements has. You have a periodic table with you. You look at the group number. So since this is what group 2, you can say, oh, most likely this has 2 valence electrons. Oxygen, on the other hand, it's in group 6. So most likely you're going to put there 6 electrons. Okay. So it has what we call valence electrons. So what happened? So what happened? You're going to lose this electron. So that goes there. And that goes on this side. So what happened to your calcium? After you lost 2 electrons, it becomes positively charged. Okay? And on the other hand, your oxygen, it gains 2 electrons. That is equivalent to 2 minus. Or the way that they put it, they can do it like this, or they put it in a bracket to show it like this. Showing you that the calcium lost electrons, which was gained by oxygen. So usually this is how you the Lewis symbol for ionic compound. Now, let's look at the energetics. Okay, there are energy that is what we call accompany these changes that we have. Although the main topic or basis for that discussion will be on chapter 6, our last chapter. Let's see how the energy is involved in this transformation. Okay, so remember, to remove this electron, there's an energy associated to that, and that is your ionization energy, which we discussed last time. Now, on the other hand, to put the electrons to the nonmetals, there's also an energy associated to that, and that's what we call electron affinity. So what we're going to do, we combine the ionization energy and the electron affinity, and we found out still endothermic. So what does it mean? You still need energy. Now, why is it endothermic? So if you're going to remove electron, you need energy to do that. If you're going to put an electron in a neutral non-metal, you also need energy on that. That's why energy is being input. That's why it's endo. Okay? So as of now, you could say endothermic is you need energy to the system. Okay? Or the process requires energy. However, They found out when the two ions bond, more than enough energy is released, which means you have an exothermic energy. So how come you have a calcium, okay, that forms into calcium 2 plus, you need energy, and then you have an oxygen, no, not that one. You need energy when the electron is introduced there, but when they form the calcium oxide, there's much energy that is released, or the overall process is exothermic. So that means there's an excess heat that was formed. So what is missing here? So the one that's missing here is the so-called lattice energy. So this is the change in energy that occurs when an ionic solid is separated into gas phase ions. It's difficult to measure lattice energy directly. So what we can do is we do the so-called Hess law, wherein you add all the processes, okay, to determine the energy changes in each steps. So just like to show you how an ionic compound form. So we're going to use your NaCl. That's the most common overused example of ionic compound. So what do you need in the NaCl? You need sodium metal and chlorine. Okay. Now they found out, okay, when they have 1 mole of Na and 1 mole of chlorine, it's going to release 639, negative 639 kilojoules of energy to form 1 mole of NaCl. Okay? So, how did they end up with this 639? So they found out the first thing for you to do is to ionize both your sodium and your chlorine. So in doing that, you're going to need 147 kilojoules. So that's the endothermic part. Okay, that's include the ionization energy where Na becomes Na plus, and the electron affinity where your chlorine becomes chloride. Now what happened next? For you to convert the Na plus and the Cl minus to NaCl, this is the amount of energy that you're going to use. And you can break it down, okay? Because before you become an NaCl, what you do is you become the so-called ion pairs first. So it's a two-step thing here. One involving this amount of energy that is released and one involving this amount of energy. Now, how do we end up with 639, negative 639? It's 147 plus negative 786. So you will have. I can assure you there's no calculation at least in this chapter. So your quizzes that you have tomorrow and going to Friday, you don't have calculation. Okay, this type of calculation will go back when we go to chapter 6. Or we can also do it instead of 786 here. So we have 147 plus negative 493 plus negative 293. And it should give you 639. So this is the process that usually most ionic compound do. The neutral atom is ionized, okay? Electron affinity to become an ion and ionization energy to become cation. And then from that, they form into this ion pair and they produce the what we call ionic compound. And that's the lattice energy. Okay? Now, this process of finding the lattice energy indirectly from the thermochemical equation is called the Born-Haber cycle. Okay? Now, if we're going to look at what's the factor that affect the so-called lattice energy, because if you're going to look at the properties of ionic compounds, typically they're high melting point. So that means they're stable. That means if you want them to melt, you're going to apply high amount of energy. So Coulomb's law, which is more on physics, that summarizes the factors that affect the strength of the ionic bond. And if you're going to look at this, it's this Q1 times Q2 over R. So what does it mean? The higher the Q1 and the Q2, the higher is the energy that you have there, the force that hold them together. Or the lower the R there, the higher is the F. So what does this mean? What's the Q? The Q is the ionic charge. So the more positive charge that you have, most likely the stronger is the attraction of forces that you have. The smaller the ion, the stronger is the force. So if we're going to apply this concept, so maybe we can make a comparison between NaCl and MgO. Okay. So which of them would have a high melting point? So if you're going to look at this, this is what? A positive 1, a negative 1. This is a positive 2, a negative 2. So if you're going to look into the charge, your MgO is 2 times, okay, the charge of the ions compared to the NaCl. So we could say it's 4 times stronger, okay? Because both the the positive and the negative charge is 2 times. So if you're going to what we call take that into effect, it's 4 times stronger because the charge double in each ion. Now, if you're going to look at the size Na plus, compare it to Mg2 plus, okay, you lose 2 electrons in Mg2 plus. So that means Na plus is larger than magnesium 2 plus. Now, in terms of chloride, compares to oxygen, okay, because the distance of magnesium and oxygen is smaller, then the distance between Na plus and Cl minus, the force between the Mg2 plus and O2 minus will be greater. Okay, so Na plus is larger than Mg2 plus, and then chloride is also larger compared to O2 minus. So in that case, the Q1 and Q2 is larger, the R is smaller, so there is a stronger force of MgO compared to NaCl. And what's the evidence to prove? To prove that MgO indeed is stronger than NaCl. Okay, if you're going to look at their so-called melting point, NaCl is at 801 degrees Celsius, while magnesium oxide is 2200 or 2800, not that one. So the melting point is the evidence that the MgO, which has a higher charge and smaller distance between one another, is much stronger in force compared to the NaCl. So maybe that's type of the questions that we're going to have. So you just look at the charge. So the one that has the higher charge, most likely that's the one that's the stronger one. Now, we have this so-called notion that when the Na becomes Na plus and the Cl becomes a Cl minus, both of them, okay, in their ionic form has a noble gas configuration. So let's try to write now, okay, the electronic configuration of this, say, ionic substances or ionic or ions. So when we examine the electron configuration of the main group ions, we find that each element gains or lost electrons to attain a noble gas configuration. So for instance, the chloride. So if you're going to look at the periodic table, its atomic number is 17. So you can start by looking at the what we call the period. So you have the third period and then the fifth element on the p orbitals, and then bring down everything. And then you add this. So this is 16 plus 2, 12 plus 5, that's 7. So if it's a chloride, okay, what will happen? Anyone? So you have a negative charge. So that means you have an additional electron. And this now becomes 3p6. And what noble gas has the same configuration? What's the one beside the element chlorine? Anyone? If you have the periodic table. If you have the periodic table, okay, the one beside the chlorine or the noble gas beside chlorine is argon. So the term that they use is if you have the same electron configuration but different ions or element, it's isoelectronic. But we will have things about this later on. Okay. Now, if you're going to look at some of the metals, some of them, they have different ionic charges. Remember the Roman numeral way of writing in chapter 2? Okay. So if you're going to look at this, one of them has a reading that is equal to the group number, and one of them that is 2 less than the group number. So if you're going to look at the notion, why do you have that? So it has something to do with the S subshell. That's why there's always a difference of 2, because S can only have 2 electrons in an orbital, in the S orbital. So the higher charge is due to the loss of both the S subshells and the P subshells electron. The lower charge is just due to the loss of only the P subshells electrons. And you always observe this either in group 4A or 5A, because tin and lead has a positive 4 and a positive 2. Because if you're going to look at that, they usually has this. So where is that positive 2 when you lost an S subshell? And when is the what we call the positive a positive 4 when you also lost the 1 in the p orbitals. Okay, so the one that is lost first is the p, okay, and then the other one is the what we call 2. So you can do it also in ns2 and p3. So if you have a plus 3, that means you lost all the electrons in the p orbitals, and you have an s. You lost also the electrons in the s orbital, so that means you have a plus 5. Okay. Now, how about the polyatomic ions? They are usually hold together by a covalent bond, but as a group, they also lost or gain one or more electron. So you treat them as a whole. Okay, so for instance, the permanganate. So within them, you have what we call the covalent bond. But as a whole, if you pair it, let's say with K, so what will happen? The K will lose the electron and the whole permanganate will gain it. So you will have KMnO. So if you're going to look at this, this is the positive charge there, and the whole permanganate is the negative charge. Okay. Now transition metal is a little bit complicated, but if you're going to look at this, most of them they have a positive too. And the way that explanation why most of them has a positive too, because the electrons that's lost is in the s orbital, not on the d. So for instance, if you are asked to give the electron configuration of Mn and 2 plus, okay, so what is the atomic number for that? 25. So if it's a 25, so you could say you could start with 3d5, and you have 4s2, 3p6, 3s2, 2p6, 2s2, 1s2. Okay. Now, what does it says? If it becomes a charge, the one where it lost electron is the s electron. So if you're going to what we could follow that notion, so that means this is the one that becomes 0. So you have the 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Because you lost the 2 electrons from the s orbital. So this is now the ionic configuration or ionic electronic configuration of your sample, your Mn2 plus. Now, what does it means now? So we discussed the so-called atomic radius during our what we call trends in periodic table. So how is atomic radius different from ionic radius? So atomic radius, if you have a neutral atom. Ionic radius is when your atom becomes charged. Okay? So it's a measure of the size of the spherical region around the nucleus of an ion within the electrons are most likely to be found. While ionic radius, like atomic radius, can be somewhat arbitrary, you can measure in ionic compounds. So for instance, what happened to the cations? So since they lose electron, they tend to be what? Smaller. If you have a positive charge, your ionic radius is smaller compared to your atomic radius. Now, an ion is always larger than a neutral atom because you gain an electron. Okay? So if you're going to look at this difference between the ions, the cation will always be smaller, while the anion will always be larger than their neutral atom counterpart. And as I have told you, okay, if they end up having the same number and configuration of electron, the term that we use there is isoelectronic. So earlier I told you, okay, chloride is isoelectronic with argon. The same thing with this one. Neon, sodium, and fluorine are isoelectronic. All of them has this configuration. 1s2, 2s2, 2p6. Whether it's a neon or Na plus or F minus, they will have the same number and configuration of electron. Now, what information we can get if we have an isoelectronic series? The ionic radius for an isoelectronic series decreases with increasing atomic number, which means if we're going to do it in terms of the size here, decreases with increasing atomic numbers. So the smallest we could say is neon. So chloride is bigger than Ne, and that is bigger than Na plus. Why? Because there's an increasing atomic number from left to right. And it says there, the ionic radius decreases with increasing atomic number. Or we could put it like this. So how are you going to arrange them in increasing ionic radius? Okay. So if you're going to look at the periodic table, the arrangement that you have here, you have what? 38 strontium on this side, and then you have Se, if I'm not mistaken, that's 34. And then in the 35, you have your bromine. No, not 38, 36. So that's the trend in the atomic number. So if you're going to look at this, so we could say, if we arrange them, strontium has the highest atomic number, and that's the smallest. Okay, followed by the bromide, and then Se2 plus. So this is how you arrange them in increasing atomic radius. No, it's 2 minus, not 2 plus. So today you can answer questions like that. Okay? Now, we now go to the covalent bond. So unlike ionic bond, which is the loss and gain of electron, covalent bond is some sort of a sharing of electron. And to consider how a covalent bond forms, we can monitor the energy of two isolated hydrogen atoms as they move closer. So if you're going to look at this, as they move closer, okay, the distance decreases. So we could say here, two isolated hydrogen atoms. So as they move closer, the distance decreases gradually and then more steeply, okay, to a minimum. And as the atoms continue to move closer, it increases drastically. So what happened here? So most likely, since you have here what? Electrons, and both of them are negatively charged. So at this point, and maybe at this point, there's a repulsion. But there's a certain distance where you have the minimum. And that's what we call the bond length that you have. That's distances where you form the so-called covalent bond, like this one. Okay? So the distance between the atoms where the energy is at minimum, that's what we call the bond length. And most of the electrons that are sharing, they have this thing. Okay? So if you're going to look at this, this is what happened. When you have hydrogen atoms move closer together, the electron of each atom is attracted to both its own nucleus and the nucleus of the second atom. Okay? Now, there is a way to represent them in the Lewis electron-dot formula, and I think it is more useful in the covalent one compared to the ionic bond. Because when you have an electron pair, it's represented by two dots. And an electron pair that is between two atoms is a bonding pair. It can also be represented by one line. So you could say it like that's like this one or that one. So that's your bonding pair. So electron pairs that are not bonding, okay, are known as non-bonding pairs or the lone pair electrons. So based on this so-called bonding pair, you can have what? A double bond, a triple bond, and a single bond. So you have single, so that's two electrons that are involved that is being shared. Double, so that means you have four electrons that is being involved. And then triple bond, you have six electrons that are being shared. And double bonds form primarily with carbon, nitrogen, and oxygen. Triple bond usually is carbon and nitrogen. Now, there is a special type of this so-called covalent bond, and it is known as the coordinate covalent bond. So, the coordinate covalent bond form when both electrons of the bond are donated by one atom. Okay? So, the two electrons forming the bond with the hydrogen here on the left were both donated by the nitrogen. And one shared, they are indistinguishable from the other NH bonds. Okay? And when you have these coordinate bonds, like the one that form here, okay, it's like the electrons are donated by one atom. That's a special type of this, what we call covalent bond. Okay, so as you could see here, you don't see an electron here, but when you bind it with the ammonia, okay, you form a bond that is indistinguishable from the other NH bond. So you cannot distinguish among here where is the hydrogen that you bind it with. Okay, so that's what we call the coordinate covalent bond. Now, in all the discussions that we have, whether we have ionic compound or covalent compound, okay, the name of the game is you have 8 electrons that is similar to the noble gas in your valence shell. And this is what we call the octet rule. The only one that is exempted here is the hydrogen and the helium. They can only have an s orbital, so they can only have at most 2. So they follow what we call the duet rule. Okay, when you have 2 singers, you call it a duet. So the same thing that you apply here. Okay, so I discussed already this to you. So how about if we have the so-called polar covalent bond? So covalent bond forms when electrons are shared. Now, there comes a time in which the electrons that's being shared, or the bonding electrons that's being shared, spend more time near one of the atom rather than the other atom. So for instance, if it's fluorine here, you could say that the atoms are equally shared. But what if it's HF? What happened here? So they found out if this is HF. So here you could say you put have an electron cloud like this one. But if you have it here, you could say that it's like this one. the electron spent more time in the fluorine. So that's what you call a polar covalent bond. And you only observe it if you're sharing electrons between elements that are not identical or not the same. And there's what we call way to know this polar covalent bond through the concept of electronegativity. So electronegativity, this is just a measure of the ability of an atom to draw bonding electrons to itself, or the ability of atoms to attract electrons. Electronegativity is related to ionization energy and electron affinity that we discussed in last chapter. And if you're going to look at this in terms of the value of electronegativity, so fluorine is the most electronegative. Okay? And just like ionization energy, electronegativity increases from left to right and from bottom to top, or decreases from top to bottom on the periodic table. And fluorine, oxygen, nitrogen, and chlorine, they have the highest electronegativity. Now, how do we know this difference in electronegativity? So if we have, let's say, FF, so all you need to do is get the electronegativity of that and then subtract it. So you don't have what we call difference between the two. So that means they shared the electrons equally. But if you have, let's say, HF here, so what you have, 4.0 minus 2.1. So there's a degree of separation here of around what, 1.9? So that means the fluorine, okay, abstract or attract the electrons more compared to the hydrogen. And it means also that this covalent bond is polar. Here, when there is zero, we could say it's non-polar. Okay? But that's just if you're dealing two atoms. If you want to determine the polarity of two atoms. So the difference in electronegativity between two atoms in a bond is a rough measure of bond polarity. So when the difference is large, you could form an ionic bond. When the difference is large, the bond is polar. When the difference is small, the bond is nonpolar. So for instance, let's look at NaCl. What's the electronegativity difference of NaCl? So you have the 3.0 minus, okay, what's Na? 0.9. So that's around 2.1. Okay, so we could consider 2.1 as what we call ionic compound already. I think they set the number difference as 2. If it's more than 2, then you have an ionic bond. Okay, so if you're going to look at the electronegativity difference here between the following bonds, so all you need to do is you have this one. So if you have a questions like this, most likely you'll be given the electronegativity difference. So if you have there between Cn, it's 0.5, NaF is 3.1, and OH is 1.4. And if you're asked increasing polarity, so the most polar here is NaF. So you start with Cn, followed by OH, followed by NaOF. So this is the one that is most polar. Analyze. Now, we go now to the main topic here, how to write the electron-dot formula. So what I'm going to do, there's a recorded version of this from last fall. I want you to look at that, because what we're going to do when we go to some of the molecules, okay, instead of using the example that we have in that record, I'm going to change that. So you will have other things to practice, okay? So you can just look at the what we call the recorded session for the one that is originally in this slide. We're going to change the example, okay? So writing the Lewis symbol or electron dot formula. So the first thing that you're going to do is determine the number of valence electron. So that means you need the periodic table to determine how much valence electron in each of the atom. And then you add everything together. And then after that, you write the skeleton structure of the molecular ion. So you try to connect them, connect one atom with another atom. And then you distribute the electrons to the atom surrounding the central atom or atoms to satisfy the octet rule. And then distribute the remaining electrons as pairs to the central atom. Okay? So what are we going to do here? So maybe we will start with this one. But as I've told you, okay, I'm going to replace it with another one. So if you want to look at the answer for this one, you can go to that other video that I posted there so that you will have more examples. Okay. So if you have water, so the first thing that you're going to do is count the valence electron on each of them. Hydrogen has one. So times two, that's two valence electron. And then oxygen would have what? 6, right? So 1 times 2 plus 6 will give you 8 electrons available. So all you need to do is account these 8 electrons. Now, if you're going to connect them, hydrogen don't obey the octet rule. It can only obey the duet rule. And then you have here, and then you have here. And all you need to do is account, are all 8 electrons accounted for? So you have 1, 2, 3, 4, and each line would have 2 electrons. So that's 4 also. So you have 8 electrons. So all 8 electrons are accounted for. So this is just like library keeping, okay? Taking into account all electrons that you have. Now, let's go on NH, not NH2, NH3. So NF3 is given in what we call the other record. So here again, you look at the valence electrons. So nitrogen has 5, hydrogen has 1, and you have 3 hydrogen. So that means 5 times 1, and then you have 1 times 3. You also have 8 electrons, so you connect them. So how many electrons has you utilized already here? So from 8 available, you have 3 bonding pairs times 2, so you have 6. So the other 2 is that. Analyze. So I'm just trying to make the example a little bit wider. So at least you who are here, you will say, oh, there's an additional example that we utilize compared to if you just watch the video. The original video. I mean, the video with the original slides that we have here. Now, instead of using this one, what if we use methanol? So what are we going to do? The CHO. So you have 1, okay? uh, hydrogen is 4, and then oxygen is 1, and then you multiply them. So this is the number of atoms, and then you multiply them with the valence electrons that they have. So 4 for carbon, 1 for hydrogen, 6 for oxygen. So overall you have, so this is 4, this is 4, this is 6. So there's 14 hydrogen, 14 electrons that you need to account for. So how do we do that? So maybe we put it like that. So you accounted 2 already. Subtract it from 14, there's still 12, and then you connect this one with hydrogen. So that's 1, 2, 3 times 2, that's 6. So you still have 6. So you still have 1 hydrogen unaccounted for, so minus 2, so you still have 4. And then you have this one. Now, the rule that they have there is each one of them follow the octet rule, or in the case of the hydrogen, the duet rule. So if we're going to look at this, so that means the oxygen should have 8 electrons. So does it has an 8? So 1, 2, 3, 4, which is the lone pairs, and then 2 bonding pairs times 2. So you have their 8 electrons for oxygen. Now for the nitrogen here, 1, 2, okay? And then you have 3 bonding pairs times 2, that is 6 plus 2, that has 8 electrons. Now the same thing that we have here, carbon and oxygen. So the carbon there's 4 bonding pairs. So each bonding pair has 2 electrons. So 4 times 2, so that means this is 8. Oxygen, there's 4, that is a non-bonding pair, and 4 in the bonding pair, so that is also 8. Analyze. Now here, instead of doing CO2 and HCN, I'll just simplify it like CO, and then this one, I do it as Cn minus. So if you have CO, so there's 1 in each of them, and then multiply it with the respective valence configuration, so 4, and then this is 6, so you have 4 and 6, so that means you have 10 electrons overall. So what you're going to do is you share it, okay, between the 2 atoms. So in this case, you could say it, you start with, said, okay, how about here? So I have 10, 2 of them was used to, I still have what we call 8. So can I put it like this? So what's the problem with this one? Yes, I have the 10 electrons here, but the problem, I only have 4 here and I have 8 here. You can share more than 2 electrons. So what if another 2 electrons was shared here? I make it like this one. So I have it like this and this one. So what will happen? I have 6 here, I have 8 here. So that means I still have to share more electrons. So I end up doing it like this. So I have 6 electrons being shared plus 2 there, giving me 8 electrons for oxygen. 6 electrons of carbon being shared plus 2 there, that's unpaired, you have that. So this is the Lewis structure for CO. Okay. Now, how about Cn minus? What happens if you have a charge? Then you treat the charge as an electron. If it's a negative, plus. If it's a positive, minus, whatever the number of the charge. So if I have it here, so both of them 1, so this is 4, and this is 5. So that means I have 4, I have 5. Since I have a negative here, okay, so that means I'm going to add 1. Because a negative charge means there's 1 electron that's available. So that means I also have 10. Okay, and I would say I'll just follow the one that I have here. But since there's a negative charge, I put the bracket. That means the whole negative charge applies to a given molecule. Question? Now this one, maybe I'll use this one because this is just to make it clear for you with the one that has a charge. So PCl, so 1 times, if you're going to look at the phosphorus, that's 5. And then you have 4 times 7, so that's 4 times, so 28. And since you have a positive here, so that means there's a negative 1. And if you're going to add together, this is what? 32 electrons. That is all accounted for. So if you're going to do it here, so how many electrons did I use? So from 32 electrons that's available, I use 4 bonding pairs. So 4 times 2, that is 8 electrons. So I subtract it. So I still have 24. And then what will I do next? I distribute 6 electrons in each of these chlorine. So 6 times 4 will give me 24. So this is the Lewis structure that you have. Now, how about the other one here? The same thing. So I have 1, and then I have 6. So I multiply that with 5. I multiply it with 7. So 6 times 7 will give me what? 42? 36? Yeah, 42. And then you have this one. So that's a positive one because you have a negative charge. So this is overall 48. And the same thing that I do, I'm going to try to connect with chlorine. So I have 6 bonding pairs. So each bonding pair is 2. So that means minus 12. So I still have what? 36. And then in each of these, I'm going to put 6 electrons in each chlorine. So 6 times 6 is also 36. So this is my Lewis structure. Now the question that you're going to be asked would be how many bonding pairs and how many lone pairs do you have? Okay. And you might also question me here, Professor, you said it should be 8 electrons at the most. How come this one? Your phosphorus has how many? 12 electrons, but there's an explanation on that as we go on. Okay. Now, what are the type of questions that are being asked? Maybe you're given this and you are asked how many bonding pairs and lone pairs does a chlorine has? So chlorine would have what? 1 bonding pair and 3 lone pair. So each of these is a lone pair. Remember, pair. Pair is always by 2. Okay? So you can have 3 bonding pairs and 3 non-bonding pairs. Maybe that's the appropriate term that you have there. And you may be asked, given this, how many bonding pairs does phosphorus have? Okay? So this will force you to write the Lewis structure to be able to answer the question. Okay? So analyze. Before we go on this so-called resonance. So in the resonance structure, they said this is due to the so-called delocalized bonding. So this is a type of bonding in which a bonding pairs of electron is spread over a number of atoms rather than being localized between 2 atoms. So instead of the electrons being stationary in a given atom, what happened is they're spread out. Okay? So that means there is more than one Lewis structure for this type of what we call molecules. We call them the resonance. Okay? And if you're going to look at the resonance structure, neither of the Lewis structure is the correct Lewis structure. The correct Lewis structure is the average of the what we call the bonding pairs that you have. So for instance, the example that we have here, instead of using this one, let's try to use ozone. Okay? So what is the valence electron of ozone? So that's 3 times 6. So you have there 18. So how are you going to connect that? So 18 minus 4, that's 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now, does this satisfy the octet rule? Yes for this, but you only have 6 here. So whenever you have less of the octet number, the best thing for you to do is to share any available lone pair that you have. So that means I can do it maybe like this. And in this case, I will have a Lewis structure like this one. But as you can see, I can move the double bond on the other side. Now the question is, which is the correct structure? Okay, the answer to that question is neither of them is the correct structure. The correct structure is the average of both of them. Why? Now, if you're going to look at this, there are 2 bonds here, right? So let's say bond 1 and bond 2. Bond 1 and bond 2. Now, experimental evidence shows that the bond length of bond 1 is equals to the bond length of bond 2. So that means the real Lewis structure is the average of these 2. So how do they end up with the same bond length? So all you need to do is count the bonding first that you have. So this is what? 1, and this is 2, and this is 2, and this is 1. And then you add them together. So you have what? 1 plus 2, 2 plus 1. And then divide them by the number of the structure that you have. You have 2 structures. So you end up both of them having 3. over 2. So that is the resonance structure. So the correct structure here is the average between the two. The Lewis structure that you write in the resonance, they doesn't exist. Just like if you, what we call crossbreed some animal. Okay. So what happened if you, what we call crossbreed a horse with a donkey? What do you get? You get a mule, right? Now, what if you're going to crossbreed, let's say, a dragon and a unicorn? What do you get? Because I think this one, both of them exist, and also this one. But as I've told you, the resonance structure that we write doesn't exist. The one that exists is the average of these two. So both dragon and unicorn don't exist. But if you going to hybrid them, there's an animal that exists that can result from it. Okay? So that is the real resonance structure. And what do you think is that? The rhino. Okay? So that's what we call resonance structure test. You just write what is the possible resonance, what we call Lewis structure that you have, but the correct or the accurate Lewis structure is the average of all those resonance structure. And if you have a resonance structure, you have to write everything. Put a double-sided arrow in it. Okay? Now, as I told you earlier, one of the example that we have PCl6, it is more than 8 because there's always an exception to the rule. And here are some of these exceptions to the so-called Lewis structure. So some molecules have electron-dot structures that do not satisfy the octet rule. Okay? In fact, the only one that you need to make sure that they have 8 electrons are these 4 atoms, CNO. Okay? Or we could say PONC. Fluorine, oxygen, nitrogen, and carbon. The others, they can have less, they can have more than 8 electrons. And in some, even though we say there are what we call the strict followers, there are some that has the so-called odd number electrons. These are what we call the radical. But we'll focus more the one that has few or more. The one that has less or more number of the so-called octet rule. So the first one that we could say is the less one. Like this one. So these are atoms in the period, in the second period before carbon. So they can occupy, let's say, less than 8. And some of you may ask, like for instance, this one. How about we do it like this? because you have now the notion of this so-called octet rule. Wait, I'm just going to. What if we do it like this? Hmm. So if we do it like this, you satisfy the octet rule. But there's a big problem on that. What can we say about the fluorine? Fluorine is the most electronegative atom. And being the most electronegative atom, it wants its electron to be with itself. It's a selfish atom. It doesn't want to share the electron. Because if you have a double bond, that means you're sharing more than two electrons. And since boron is below carbon, it's okay for them to have less than 8 electrons. So that's the exception there. Okay? So you cannot apply here that says, oh, it's a resonance and it is this, because fluorine, being a selfish atom, it doesn't want to share its electron. Okay? Now, how about the one that has what we call the more than 8? So usually it's the S and the P that we have in our example, and then the Cl as the central atom. Now, the main reason why they can accommodate more than 8 is usually this is in the third period, and in the third period, okay, in the second period, you only have S and the P. But in the third period, you have the S, you have the P, you have the D orbital to accommodate the extra electrons that you have. Okay? So that's the reason why you can have more than 4 electrons. So let's try to do, instead of this one, I think SF6 is the safe bet for that. Although I'm going to try to use other example that we have. Let's say SF6. So if you're going to look at the SF6, you have what? S, that's 1, F, that's 6. And then if you're going to look at the valence electrons, so 6 times 7, so that gives you 42. And then 1 times, what is the valence electron of S? So it's the same as the oxygen. So you have 48 overall. So the way that you're going to do it is S, you have F, 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 F. So you have 12 USS bonding pairs, and then in each of these, you have 6. So you have 36 there minus 36. So this is the materials that you have. Now let's try another one. Let's say Xe F4. So Xe is what? That's 1 times 8. F is 4 times 7. So that's 8 plus 28. So you have 36. So you have their Xe So out of the 36, you use 8 as the bonding pair. So you still have 28. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So you still have an extra one. So what happened to the extra electron? It goes to the central atom. And as you could see here, you have more than 8 electrons in your central atom. Okay? So these are the ones that can accommodate more than 8 electrons. And then, how about the concept of this, what we call formal charge? Where do we use this so-called formal charge? So, if you have a formal charge of an atom in the Lewis formula, this is just the hypothetical charge you obtain by assuming that bonding pairs are equally shared between bonded atoms and the electrons of each lone pairs belong completely to one atoms. So if we're going to look at this as the things that we have here, I can determine the bonding pairs. So for instance, what's the what we call the formal charge that we have here for the oxygen? So we put A, B, C. Okay. So if we're going to look at the formal charge, you're looking at the valence electron on the free atom minus 1/2 of the number of electrons in bonding pairs, and then minus the number of the lone pairs electron. So remember what we had earlier, like this. Now, what can you say about the oxygen here? Are they equivalent? They're not. So that means you're going to have a different formal charge for each of these oxygen here. That's why I put here an OA, an OB, and an OC. And then all of them will be what? 6. And then I'm going to subtract based on the number of the electrons in the bonding pairs and based on the number of lone pairs electrons. So in the A, how many bonding pairs will I have here? So I have there 2 bonding pairs. So there's what? 4 electrons. Now only 1/2 of that will go to the oxygen. Now how many lone pair electrons do I have here? 1, 2, 3, 4. So what's my formal charge of my OA? Anyone? Zero, right? 6 minus 2 minus 4, 0. Now how about the other one, the OB? So how many bonding pairs do I have there? I have 3 bonding pairs, so that means that's 6. And I have 2 lone pairs there. So that means 6 minus 3 minus 2, I have a plus 1. Right? So I can put here 0. I could here plus 1. That's why I use this as an example, because same oxygen but different formal charge. Because as you can see, they have different what we call number of bonding pairs and number of lone pairs. Now the last one, you have one half, and then you only have one bonding pair. So that's 2 electrons there. And then you have what? 1, 2, 3, 4, 5, 6. So 6 minus 1 minus 6, so that's a -6. If you're going to look at the formal charge of this, you have 0, you have +1, and you have -1. And the rule that they have, just like your oxidation number, if you add the formal charge, it will give you the charge of the molecule, which in this case is equals to 0. Now you may ask yourself, where do we use this formal charge? We use this to determine which is the most appropriate Lewis structure. Okay? So formal charges can help to determine the most likely electron-dot formula using the 3 rules. Whenever you can write several Lewis structure for a molecule, choose the one having the low magnitudes of formal charges. And when 2 proposed Lewis formulas have the same magnitudes of formal charges, choose the one having the negative formal charge on the more electronegative atom. And when possible, choose Lewis formulas that do not have like charges on adjacent structure. So this is the example that we have, but I told you, look at the recording that we have because we're going to use another example. So what if we have CH2O? How are we going to write the CH2O here? One of you may write it like this. So what do you have here? 4, and then 1, and then 6. So this is times 2. So you have 12 electrons, if I'm not mistaken. Now you can write maybe one of them like this. So 1, 2, 3, 4, 5, 6. Is this the right one? Or maybe I have to do it like that one. So 1, 2, 3, 4, 5, 6. Or another way of writing it would be maybe this way. You also have 1, 2, 3, 4, 5, 6 times 2, 12. Now the question is, which is the right one? Okay. So that's where you're going to determine the formal charge definitely of your carbon and the oxygen, because I can bet your hydrogen is equals to 0 here. Why did I say the hydrogen is equals to 0? So you have 1 minus 1/2 of 2 minus 0, because it doesn't have a lone pair. So that's just equals to 0. Now, let's try to go at the formal charge of the carbon and the oxygen. So carbon has 4, oxygen 6, valence electron. So let's go here. How many bonding pairs do we have here for carbon? 1, 2, 3. So that's what? 6 electrons in 3 bonding pairs. And then you subtract it with 2 lone pairs. 2 electrons in lone pair. So that will give you 4 minus 3 minus 2. Is that -1? And in terms of the oxygen here, so that's not the one. So we have 6 minus 1/2 of 3 bonding pairs. That's 6 electrons there, and 2 electrons in a lone pair. So that will give you what? +1, right? So this is a +1, and this is a -1. Now, how about we do it this one? So you have 4 minus 1/2 of 8. There's 4 bonding pairs. There's no lone pairs, so that is 0. And for the oxygen that you have there, you have 6 minus 1/2 of 1, 2, 4 minus 1, 2, 3, 4. So that is equals to 0. So which is the correct one? We go to the rules here. Whenever you can write several Lewis structure for a molecule, choose the one having the lowest magnitudes of formal charges. Which one of these satisfies statement 1? This one, because 0, all of them are 0. Here you have a +1 and a -1. So first statement goes to the second structure. The next statement, when two proposed Lewis formulas have the same magnitudes of formal charges, choose the one having the negative formal charges on the more electronegative. Which is a more electronegative between carbon and oxygen? It should be this one, right? But look at the charge that it has. It's positive. So the second statement said, choose the one having the negative formal charge on the more electronegative. So that itself make it not the correct Lewis structure. So overall, we could say this is the correct Lewis structure. And that's where you use your formal charge. Now, what other things that we need to know here? The bond length and the so-called bond order. So bond length, or the distance, or bond distance, just as the distance between nuclei in a bond. So we have what? Single, double, triple. So if we're going to look at the bond distance here, this is the longest one, and this is the shortest one. Okay? Then in terms of the bond order, this is defined in terms of the Lewis formula, the number of pairs in electrons in a single bond. So just like this one. So this is a bond order 1, 2, 3. So bond length decreases as the bond order increases. So for instance, why do you think N2 is the most stable substances? When it goes to our body as N2, it will go out of our body as N2. And that's the problem that we have, because N2 is so stable. You can only break N2 if you have some lightning, or the power equivalent to a lightning. So whenever they said lightning strikes, there's a mushroom that will sprout. Because what happened, okay, the lightning will break down the N2, and it can be assimilated by some microorganisms or organisms. Okay? And that's the reason why the nitrogen in our body is being supplied by the plants, because they're the only one that can fix nitrogen in the atmosphere. I'm not sure if you heard this nitrogen fixing bacteria. So they absorb the N2 and convert it to other form of nitrogen. And the main reason why nitrogen is so stable is because you have a triple bond. Okay? It is a high bond order. Now, the last portion that we have here, I'm not going to have a calculations like this, but when you take your orgo, you're going to have some calculation like this one. The thing that they're telling you here is, at least if you see a bond order like this one, or a bond length, or a double bond like this, you expect it to be shorter compared to, let's say, the bond length here. So one carbon-carbon bond has a length of 150. So all of these are 150 picometer, and this is a 134. So identify each bond with the bond length. So maybe we could put it like this is the one, and this is the one that you have here. It's a carbon-carbon, okay? This one is not included. It's just these two here. So this is the 150 and this is the 134. Now, as I told you, the bond energies associated to it is the average enthalpy change for the breaking of A and B, AB bond in a molecule in the gas phase. And the way that they look at it, a bond order is a measure of bond strength. The larger the bond energy, the stronger is the bond. So if you want to determine the heat of formation or enthalpy change in terms of bond energy, that's just equals to the sum of the bond energies for bonds broken minus sum of the bond energies that are formed. When delta H is negative, it's exothermic, heat is released. When delta H is positive, it's endothermic. That means heat is absorbed. So trying to do that, we're not going to have this in the chapter quizzes and the exam, okay? But I just need to discuss this to you. So if you have this reaction, so as you could see here, there's a breaking of the double bond to form a single bond, okay? And in addition to that, you also form a bond with chlorine. So the bonds that is broken here is the double bond of your carbon and the bond that hold the chlorine together. Now the bond that is formed, okay, is the single bond and the two carbon chlorine bond, and it's equivalent to this amount of energy. So you are asked, what's the enthalpy change here? So as it mentioned there, the enthalpy change is just the bonds that's broken minus what? The bond that is formed. So all you need to do is add these two or subtract this with this one. 842 minus 100, 1000, giving you 158. Okay? So that's the coverage that we have. And we're going to continue about Lewis's structure in the next chapter. So it doesn't end here. Okay? We still what we call going to use Lewis's structure in our next meeting. I'm trying to look at the what we call the questions that we have in the exam. I'm trying to open the file. Where is it? Where is it? Trying to share. So do you see the thing? So what are the possible questions that can be asked here? So as I told you, there will be no calculation problem. Although if you could see some calculation problem in the example, just ignore it. Okay. So here you might be asked which of the following has the most ionic bonding. So all you need to do is find, okay, uh, what we call the main difference in the electronegativity. So the choices that I have here would be the first three. Okay. So usually the farther they are from one another, the most likely the higher is the difference that they have. So you need the periodic table to determine the difference here. And then this one, which of the following compounds would be expected to have the lowest melting point? So you use the Coulomb's principle. So the one that has the highest charge may be the one that will give you the highest thing. So if I'm not mistaken, I think the answer here would be letter B. B or C? I think it's C because you have there a 3 plus from this one. So which of the atom has the Lewis dot symbol? Okay. But I'm trying to look at least the one that has the Lewis structure. So this one. So this is the one that I told you that for you to answer the question, you have to write the Lewis structure. So you may have questions like this. It can be like this also, okay? So these are the type of questions that you can expect to encounter during the quiz. So I want you to go over those practice exam